Hey guys, Max here. I'm going to show you guys my planar constraint. The point of this guy is that you have these pins here that exact normal forces on the square block. You can kind of see where you can push this square block and place the pin so that it doesn't move. Some forces are zero, some of the moments are zero. So my initial design, I want to make a design where I didn't have to drill that many holes, manufacturing time is low, find parts that are easy to scavenge. So that led me to the MIT MakerWorks, where I found some ABS plastic, some aluminum cylinders, and I went to work. So I milled these slots here and then these holes here, and so that lets me move these pins around. I can kind of put them in positions I want, and so I don't have to make like multiple holes for multiple constraint designs. So that's really neat. So when I first started, I kind of thought maybe I can constrain this guy with 2 pins. So that's what was my first analysis. So I took 2 pins and I put them on the sides. Well, this is all on paper. So basically when I did my analysis, I found out that to constrain this guy, to have any chance constraining this guy with 2 pins, they both have to be, if you draw the origin here, this is plus y, this is plus x, they both have to be either double positive right now or double negative. And so now that they're both double positive, I can push at 45 degrees, and that's constrained, but if I push any other way, it kind of rotates. So, and then I'll show you if one is positive, one is negative, how it doesn't constrain it. There's no way to constrain this guy. Anywhere I push, because one's positive, one's negative, it doesn't work. So that kind of led me that you can't really constrain with 2 pins. Just because you have to push, they have to be in like one position, you have to push it exactly, but as soon as you change positions, push the same force, or you push with a different force, in a different direction. I also want to note that I'm only modeling if I'm pushing the force at the center, and I'm only pushing forces within 180 to 270 degrees. 180, 270 degrees, this is the plus x origin, plus y origin. So, in summary, 2 pins doesn't work. So I went to 3 pins. So originally my intuition was that you should probably locate these pins on the edges. So I had 2 pins on the edges, and then I had this 3rd pin. My initial calculations actually told me that I can place this 3rd pin anywhere on this face, and it'll have the same effect. But after popping into my MATLAB model, I found it's not true. I found that you kind of have to have the pin right between these two guys, right in like the center to the edge, because or else you're just gonna get a lot of non-constraint. But if you move this guy over here, really great how I can do this all with one hand. Move over here, it works for some angles, but not for other angles. Not that one. See, around like 180 to like 225 degrees doesn't work. And my model actually showed me that, so that was kind of cool, seeing the correlation with the model. So after working with the model, I kind of found the ideal 3-pin position to constrain from 180 to 270 degrees. That was, so the pin, the 2 sides, the 2 pins on one side, the one should be on the outermost edge, and then this guy can actually be anywhere within right here. So I can put them right here, right here, right here, right here. I'll zoom right here. And then the last pin should be in the middle of the y axis. So in line with the origin. So in line with the origin. This guy on the edge, this guy right here. And it's actually constrained in all direction, 180 to 270. No matter how I push this guy, it doesn't move. And my model told me that, which is pretty neat. So this is kind of cool. This deals with forces applied from the center, but what about forces applied from the side? Whoops. 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 Oh, that's good. Oh, that's good. That's good. That's good. So basically, I found out that for force applied from the side, if you're applying it this way, they have to fall between these 2 pins. So here is okay, because it falls between two of these pins. So this is all nice and dandy. But once I push outside that pin, rotation. And then applying forces on this side, since there's only one pin here, I had to apply it directly to the pin. I can't apply it here or here. If I apply it here, rotation. If I apply it down low, rotation. If I apply it right on point, we're good. So the only way to constrain external forces with the pins is you have to actually use 4 pins. So you put them on the edges. This kind of is like if I took just like a bar and I put it right here, whoosh, it kind of has the same effect, but I guess you have less material to constrain with, which is always nice. And so if I do this, oops, I pulled on that. Bang, bang. So that's how you totally constrain through all external forces. And then I showed you with how to constrain through the force in the middle. So for the 3 pins, I actually had this hypothesis. I'm not sure if it's true, but I'll just lay it out here. If you want to, first of all, for this guy, you only can constrain if your line of force from the center falls between your 2 outermost pins. So if I put this, so right here, I push here, it's actually in the 2 outermost pins, so it constrains. But if I push, well, not in all circumstances, I think there's like an angle here where it doesn't constrain totally. See right there? If I push like 180 degrees to 225 degrees, it doesn't constrain. Yeah. And then, so you have to push within these 2 guys, and then you also have to push within these 2 guys. So these all work. Not if you push this way, but these all work, but this shouldn't work. Yeah, there's a little rotation. Anyway, so like that's the line of force for through the center. That's kind of a theory. I think it's right. But yeah, so here's a planar constraint. Hope you guys liked it. The ABS on ABS was a great idea. Very low friction. It's like a suction air bearing right here. Really proud of it. Alright, this is Max signing off. See you later.